Hello, this is our second video concerning the definition of infinite series. In this video we're going to investigate why series with non-negative terms are in some sense a little easier to work with and see some examples to kind of illustrate the points we have here. Now, in the first video we defined the sum of an infinite series. So the infinite series summation k runs from 0 to infinity a sub k is defined to be the limit as n goes to infinity of the summation k equals 1 to n of a sub k, and as we saw in the last video, we're going to use the notation s sub n to denote this sum from 1 to n. This is called the nth partial sum of the series. Now this limit will either exist as a finite number or not exist. So if the limit in 1 is equal to a finite number s, then we're just going to say the sum of the infinite series is s. And if that limit does not exist, or is plus or minus infinity, then the infinite series diverges. So we're going to spend a good deal of time in our study of series working with infinite series of non-negative terms. That means an infinite series of non-negative terms is an infinite series, summation k equals 1 to infinity a sub k, where the ak's are all non-negative. Now, this actually makes our life a little easier. For such an infinite series, for any n bigger than or equal to 1, nth partial sum Sn, we get that by adding a1 through an together, a bunch of non-negative numbers. And we're going to just do a very simple inequality here. Here's the a1 through an added together again. I just grouped them in parentheses. And if I add one more thing to it, because this a sub n plus 1 is greater than or equal to 0, that'll give us something possibly bigger, but certainly not smaller. And if I add one more term, of course, I'm at Sn plus 1. So in other words, if we add the non-negative number an plus 1 to Sn, this gives us something larger, and this larger quantity happens to be S sub n plus 1. So what that means is that since this is true for any two consecutive terms of the series, what we have shown here is that the partial sums S1, S2, S3, etc. get bigger as we move out in the sequence of partial sums. In other words, the sequence of partial sums is a non-decreasing sequence. We talked a little about non-decreasing sequences when we studied sequences, and we'll see that our results in that case have an important consequence when working with series. In our work with sequences, we learned that a non-decreasing sequence of real numbers either converges to a finite number or diverges to plus infinity. In other words, it can't go to minus infinity and it can't oscillate. There's just these two possibilities. You might remember the graph like this. If we graph the sequence first, second, third, fourth, and do the SNs here, there might be a line above which the SNs can't go, although they do increase like this. And if that's the case, we know that the sequence converges. The other option was that there is no line above which these things can't go, and in that case we might have the sequence going off to infinity. But because the sequence increases, these dots have to rise from right to left. They can't go down to minus infinity, and they can't oscillate up and down. So this leads to an important and very, very useful realization for us, and that's this. Suppose we have an infinite series of non-negative terms. So again, the a sub k is all greater than or equal to 0 for all k. And then the sequence of partial sums, S sub n equals infinity, must be non-decreasing. So the sum of the series, remember, is the limit of the sequence of partial sums. And again, if the S sub n's are, there's only two possibilities: converge to a finite number or diverges to plus infinity. Negative infinity is not an option. Oscillation is not an option. In particular, if the sequence Sn, of course, is bounded above, remember the picture we drew a little earlier with the sequence staying below a horizontal line. If that sequence is bounded above, then the infinite series converges to a finite number. If that sequence is not bounded above, we saw in our earlier picture that means it goes off to infinity, then the infinite series diverges to plus infinity. So example is we're going to determine the convergence or divergence of the harmonic series. This is a very important series, one we'll see a lot of. The harmonic series is defined simply to be the summation as k runs from 1 to infinity, 1 over k, which is 1 plus a half plus a third, etc., plus 1 over k, i.e. just the reciprocals of the positive integers. Now, we're going to actually show that this series diverges to plus infinity by showing that its sequence of partial sums is increasing and bounded above. Okay. So because the terms a sub k equal 1 over k are non-negative, this infinite series either converges to a finite number or diverges to infinity. We will show that the latter is the case by showing the sequence of partial sums is unbounded. So we're going to take the following approach. For a large integer n, we're going to consider the partial sum s sub 2 to the n, and that's partial sum is given by the sum k runs from 1 to 2 to the n of 1 over k. We'll show that partial sum's at least as big as n over 2. Now, the idea here is this. We know these partial sums are non-decreasing, so S1 less than or equal to S2, less than or equal to S3, etc., less than or equal to S4, less than or equal to, we'll have S7 come in here eventually, S8, S16 will be out here, and so forth. Now, the point is we're going to focus on these ones that are powers of 2. S sub 2 is 2 to the first. S sub 2 squared is S4. When n equals 3, we'd have S sub 2 cubed up here. That'll be S8, S16, etc. We're going to show that these particular partial sums are getting big. And then because the sequence is non-decreasing, if we can show just a sporadic sum of these are big, then all the others, because we have to be increasing, have to be getting big also. So by just focusing on these particular ones, we can actually convince ourselves that the whole sequence of partial sums is unbounded. So to do that, we're simply going to establish this inequality by grouping the terms of s sub 2 to the n in a certain way and then doing some basic arithmetic. So this isn't really hard mathematics, it is a little clever. So here's what the partial sum s sub 2 to the n would look like. Again, it's just the sum as k runs from 1 to 2 to the nth power of 1 over k. We can write out this partial sum like this. 1 plus a half plus a third, keep going till we get to 1 over 2 to the n. Now, our first step is to group these things into certain subsets by using parentheses. So we're going to leave the 1 and the 1/2 out in front. We'll take the 1/3 and the 1/4 together. And then we're going to go from 1/5 to the next power of 2 reciprocal. That's 1/8 or 1 over 2 cubed. And we're going to keep grouping things like this, as we see here and here. And at the end, we're going to group down to the 1 over 2 to the n. That'll happen from 1 over 2 to the n minus 1 plus 1. Before this, we'll have grouped 1 over 2 to the power n minus 1 and some stuff before it in the parentheses. And so the last one will look like this. And you might notice here that there are 2 to the n minus 1 terms added here. In this last set of parentheses. Here we have 2 terms, 1/2 of 4. Here we have 4 terms, 1/2 of 8. And this pattern continues. In this last one, we'll have 2 to the n minus 1 terms, which is 1/2 of 2 to the n. Now get something smaller by replacing several of these numbers in each set of parentheses by something smaller. And that happens like this. In each set of parentheses, notice the last term is the smallest. So we're going to replace each term in each set of parentheses by the last term. So that means in the first set, the 1 over 2 squared is going to also replace 1 over 3. And we have 1/8 down here. We're going to put that in instead of each of these 3 numbers, etc. When we do that, we have the following. Of course, because we're making these numbers, so replacing 1/3 by 1/4, that gives us something smaller. So we're getting something smaller than S of n. Likewise, we replace 1/5, 1/6, 1/7 by the last term in the parentheses, the 1/8. That happened here. And in the last set of parentheses, everything before the 1 over 2 then gets replaced by 1 over 2 to the n. So this gives us something smaller than S sub 2 to the n. The reason we're doing that is that these terms are pretty easy to add up because in each set of parentheses they're all the same. And we're going to finish by doing that. So we have here the 1 and the 1/2 again are just going along in front there. Now in the first set of parentheses we know we have 2 terms. That's this. And each of them is equal to 1 over 2 squared. In the second set of parentheses, we have 4 terms, that is 2 squared, each of which is equal to 1 over 2 cubed. And this continues, this pattern in the last, we're going to find we have, as we mentioned earlier, 2 to the n minus 1 terms, and each of them is equal to 1 over 2 to the n. Notice all these products powers of 2 all turn out to be 1/2. There's another 1/2 right here. So it's not hard to see that there are n 1/2s coming together here. And then plus that 1 will keep on in front. And then just to make things look a little simpler, we can say this thing is in fact bigger than n over 2 just by dropping the n. So what we've showed here then is that the partial sum S sub 2 to the n is at least as big as n over 2. So when this n gets large, this gets large, showing that the S sub 2 to the n gets large. So we've now shown that the sequence of partial sums of the harmonic series is unbounded. And again, just as kind of an illustration, let's say, could we produce, say, a partial sum that is bigger than 1,000? And sure we can, and here's how we do it. We'd like n over 2 to be 1,000, so let's let n equal 2 times 1,000 or 2,000. And then according to the inequality we just looked at on the previous slide, this means S sub 2 to the 2,000th is 1 plus 1/2 plus 1/3, finally ending up at 1 over 2 to the 2,000th. So this is a lot of terms here. But according to our inequality we saw, this will be bigger than the n over 2. Again, the n was 2,000, which is 1,000. So if I add up the first 2 to the 2,000th terms of this harmonic series, and that'll take a long, long time, I know I'll get an answer bigger than 1,000. So to write our conclusion, because the terms of the harmonic series are non-negative and the partial sum of the harmonic series are unbounded, we know that this series diverges to plus infinity. So in other words, if you start adding reciprocals of positive integers, you can make that sum as large as you want if you go far enough out in this infinite series. So in this example, we replace several terms of the partial sum by smaller numbers. Remember, all was like 1/3 replaced by 1/4, the 1/5, 1/6, 1/7 replaced by 1/8, etc. This resulted in a very easy to manage sum because we were just adding a bunch of similar numbers. We knew how many numbers there were in each set of parentheses. And we showed that this smaller partial sum could be made as big as we like. So the n over 2 was easy to work with. If we want to show a sequence of partial sums as bounded above, then we may replace some of the terms of a partial sum by something bigger to manage, but still bounded, so we can say that the partial sums stay bounded. So we're going to look at an example of this, and we'll revisit the telescoping series when we do this. So let's consider this positive term infinite series, summation k equals 1 infinity 1 over k squared. So what this infinite series looks like is it looks like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. We keep going. So here we're summing the reciprocals of the squares of the integers. We'll show this infinite series converges by showing that all the partial sums, no matter how long you make the partial sums, they're all less than 2. So we're going to start by investigating the nth partial sum S sub n. So once again, S sub n, we get that by summing from k equals 1 to n 1 over k squared. The k squared we're going to write as k times k in this case. Helps us get some insight. But if we write that sum out, it just looks like this. Now, we're now going to make these things bigger, each of these fractions bigger by making the denominator smaller. We're going to save the first denominator right here. That one doesn't change. But in this denominator, I'm going to take this 2 and replace it by 1. So 1/4 here now becomes 1/2, which is bigger. In this 1 over 3 times 3 fraction, I'll take the 3, replace it by 2. And since 2 is less than 3, this is a smaller denominator and a bigger fraction. 1/9, in other words, gets replaced by 1/6. And then for 1/4, replace that 4 by 3, and again, something bigger. We can get something bigger than this partial sum by making a small adjustment to all these denominators. When you get to the last one, 1 over n times n, that first n gets replaced by n minus 1, and again, that makes that denominator smaller, makes the fraction bigger. Now, why do this? Well, because having done this, we can now work with partial fractions again. And it turns out that we can now write this as 1 plus, now again, here's partial fractions coming into play. We're going to use the expansion that 1 over k minus 1 times k can be written as 1 over k minus 1 minus 1 over k. So in other words, 1 over 2 times 1 is the same as 1 minus 1/2. 1 over 3 times 2 is 1/2 minus 1/3. 1 over 3 is 4 is 1/3 minus 1/4, etc. And of course, you see the telescoping series here. The minus 1/2 and the 1/2 cancel. The minus 1/3 and the 1/3 cancel. Minus 1/4 and a 1/4 cancel. And finally, at the end here, you'll have this 1 over n minus 1 cancel with a 1 over n minus 1 just before it. What doesn't cancel? Well, there's that one, and this 1 over n minus 1. So our telescoping expression does the following. Our S sub n, we saw, is less than this sum because we got this by making denominators smaller. And we just saw the cancellation here. The survivors are here and here, 1, that 1, and the minus 1 over n minus 1. And of course, this comes out to be equal to 2 minus 1 over n, which is less than 2. So it doesn't matter how long you make the partial sums, go as far as you like, you're always going to have something less than 2. So this is a sequence of partial sums for a non-negative term series that is bounded above. So the partial sums of the positive term series are bounded above by 2. And so that means the infinite series converges to a sum, and that sum is less than 2. So we have this, we have Sn less than or equal to 2, and so the sum of the series is the limit as this happens. And of course the limit of 2 is just 2, and this limit of Sn is the sum of the series. And so whatever this series does, it converges to a number less than 2. Now, what is the sum? Well, that's a trickier question. We won't investigate that in a calculus course, but with some work, you can actually show this sum reciprocals of squares series has a pretty cool sum, pi squared over 6. How does that happen? Isn't that cool? So now I'm going to take a look at this kind of long-winded paragraph down here. It turns out that generally, if you have an infinite series, finding the actual sum of that series can generally be very, very difficult, except in a few special cases. Those special cases are telescoping series. We've seen those work out pretty nicely. Geometric series, we'll talk about those in the next video. And then we're going to explore a topic called power series. And often if you can relate an infinite series to a power series, you can declare what the sum of that series is. But because this summing a series is so difficult, for the most part, we are going to focus on just determining if an infinite series converges or diverges. Okay, that's what we're going to mainly be interested in. And again, remember, we're looking at infinite series with non-negative terms, and this is usually done by determining whether the sequence of partial sums is bounded above or not. And so we're going to do a lot of work here with techniques for making this determination for sequences of non-negative terms. We're going to spend a lot of time looking at infinite series like the harmonic series, the sum of the reciprocals of the squares, etc., and other similar series. We won't spend a lot of time with series that have both positive and negative terms. Those are a little more difficult to determine. So we'll spend a lot of time looking at techniques to determine whether the sequence of partial sums of a non-negative infinite series are bounded above or not. Okay, what to take away from this video? So in this video, we focused on infinite series with non-negative terms. Summation k equals a sub k, where the a sub k's are non-negative real numbers. And the reason we do that is our options for what happens with the series are cut down a little with this, that such a series must either converge to a finite number or diverge to plus infinity. We can't get negative infinity, we can't get a negative number, and the sequence of partial sums cannot oscillate, so we cannot have divergence by oscillation. And this all happens because in this case, the sequence of partial sums is a non-decreasing sequence. Now, in this case, the sequence of partial sums is either bounded above, in which case the infinite series converges to some finite number, and if the sequence of partial sums is unbounded or not bounded above, then this infinite series diverges to plus infinity. We saw two examples in this video, the harmonic series showing how we can show that a sequence of partial sums is not bounded above, and the sum of reciprocal of squares series, an example of a sequence of partial sums that is bounded above. Again, it's generally pretty difficult to determine the sum of an actual or arbitrary infinite series, but for our work, it'll often be enough to just know whether the series converges or diverges, even if we can't find its sum. And so we're going to focus on sequences of non-negative terms because this determination is a little easier in this cases. If we can show the partial sums are bounded above, then the series converges. If we show that the partial sums are not bounded above, then the series diverges to plus infinity. This kind of focus on these kind of series will be the focus of our work for the next few weeks. And then we encountered one of the most important infinite series we're going to be working with. This is the harmonic series. It is the sum of the reciprocals of the integers, 1 plus a half plus a third plus a fourth, etc. And as we showed in this earlier in this video, this infinite series diverges to plus infinity. You should know this, commit it to memory. It should be an automatic response when you see this series. You can also show that this series diverges by using what's called the integral test. And that is the first test we'll look at after we finish our introduction to infinite series. The integral test is a way to take a series of non-negative terms and determine by evaluating an integral whether the series converges or diverges. Okay, so again, review this material in sequences on increasing bounded above sequences and keep straight how that plays into the infinite series picture. See you in the next video. Bye.